Okay, let's dive right into this explainer. Today, we're setting our sights on one of the most eerie, dynamic, and honestly downright captivating objects hiding in our night sky. We are going to explore a cosmic structure that has puzzled astronomers for decades, and it's still revealing incredible physics about the life cycles of stars. Welcome to our deep dive into Caldwell 56, which you might know better as the absolutely stunning Skull Planetary Nebula. So right off the bat, the crucial thing to wrap your head around here is the distance. Our target is located exactly 3,500 light-years away from us. And when we talk about distances like that in space, we aren't just talking about a location on a map, right? We're talking about time. Looking at the Skull Nebula means we are looking deep, deep into the history of the cosmos. We're actually seeing light that began its journey toward Earth right around the time the very first complex human civilizations were just starting to form. So, if you happen to look up toward the Cetus constellation tonight, you're gazing in the exact direction of Caldwell 56. This incredible object was first spotted by the legendary astronomer William Herschel way back in 1785. And ever since then, it's served as this amazing cosmic laboratory for scientists who are trying to understand the incredibly violent and strangely beautiful ways that stars actually end their lives. Chapter 1. Meet the Skull Nebula, Unraveling the Eerie Glow. Let's see how this builds our understanding of what this celestial skull actually is, because there's a lot of intense astrophysics hiding right behind that ghostly face. Now, before we go any further, it's vital to define exactly what we're dealing with here. Caldwell 56 is a planetary nebula. And, quick side note, despite the name, it has absolutely nothing to do with planets. It's a total misnomer. A planetary nebula is actually the glowing aftermath of a dying star, specifically what's called an asymptotic giant branch star that has completely exhausted its nuclear fuel and just violently shed its outer layers into the vacuum of space. And you know, this perfectly illustrates a super common point of confusion that we should really just clear up right now. In the official catalogs, Caldwell 56 is also known as NGC 246, the Skull Planetary Nebula. But it is completely distinct from a similarly named object, NGC 24067, which is known as the Skull and Crossbones Nebula. That one is an emission nebula, basically a stellar nursery where brand new stars are forming. Our target, NGC 246, represents the exact opposite end of the spectrum. It's the beautiful death of a star. Now, what's really fascinating here is the actual structure of NGC 246. It's got this slightly elliptical, really clumpy morphology. Notice how it has this glowing, bright boundary on one side, and then these darker, empty voids right in the center? That's what gives it that uncanny appearance of a floating skull. But here's the thing. That uneven, clumpy shape isn't just a random optical illusion. It's actually telling us a massive story of violent cosmic motion. Chapter 2. A high-speed cosmic collision, the interstellar speedboat. To truly understand its shape, we have to zoom in a bit and look at how this nebula is actively and violently interacting with the empty space around it. So, looking closely at the structure, a pretty obvious question pops up. Why on earth is the bright star system inside pushed way off from the geometric center of the nebula? I mean, in most planetary nebula, the dying star just sits neatly right in the middle of the gas it expelled. But here, it looks like it's been shoved all the way to the western edge. Well, the answer lies in this absolutely astonishing number, 85 kilometers per second. That is the blistering speed at which this entire system is just tearing through the interstellar medium. It is moving so incredibly fast that the central star is literally catching up to the expanding shell of gas that it blew off thousands of years ago. Think of it kind of like a massive cosmic speedboat creating a glowing bow wake on a lake. This high-speed movement causes what physicists call compressional heating. Basically, as the nebula rams into the surrounding interstellar gas at that crazy speed of 85 kilometers per second, the leading western edge of the shell gets compressed. That friction causes it to heat up and glow brilliantly. And all the while, the forward expansion of that shell is literally decelerating because it's plowing through the friction of space. Chapter 3. The Triple Star Engine, a Hierarchical Dance. Let's peel back another layer here and penetrate the core. We need to reveal the spectacular engine that's actually driving this whole phenomenon. Because the star at the center of this nebula, it is definitely not flying solo. This central engine is designated as the HIP 3678 system, and it makes Caldwell 56 entirely unique. Get this. It is the very first planetary nebula ever discovered to host a hierarchical triple star system. It features a close binary pair, that's star A and star C, locked in a super tight orbit. And then there's a much more distant third companion, star B, orbiting that pair from way further out. It's a three-way gravitational dance. And the dramatic contrast between these stars is just mind-blowing. The primary star, star A, is the remnant core of the dying star. It is a wildly hot, hydrogen-deficient white dwarf burning at a blistering 150,000 Kelvin. Literally so hot that its radiation is ionizing the surrounding gas and making the entire nebula glow. Meanwhile, its two companions are these relatively cool, low-mass dwarf stars, just quietly tagging along for this extreme high-speed ride. But before it became that 150,000 Kelvin white dwarf, the primary star was a massive asymptotic giant branch, or AGB star. It originally weighed in at around 4.3 times the mass of our own sun. Its internal structure featured a dense carbon-oxygen core surrounded by these active shells of burning helium and hydrogen. Those layers generated the intense thermal pulses that ultimately forced the star to expel its entire outer envelope. Tracing this timeline is just fascinating. You see, because the initial separation between these three stars was wide enough, they actually dodged a major bullet. They successfully avoided a completely destructive common envelope phase when the primary star swelled up as a giant. Instead, as the massive primary shut its mass to form the nebula, the gravity of the whole system shifted. This caused the entire triple star setup to shrink down to a third of its original size. So they survived the death of their main star, but the cost was being pulled much, much closer together. Chapter 4. Solving the X-ray Mystery, the Missing Shocks. Okay, let's dive into our final cosmic mystery for today. This one actually required the combined analytical power of two major space observatories to figure out, and it's where the physics gets really, really intriguing. So given the extreme 85 km per second speed of the nebula, plus this insane stellar wind blowing off the central white dwarf at over 4,000 kilometers per second, scientists fully expected a violent collision. They expected to find a massive shell of superheated, shocked gas blasting out high-energy X-rays. So why did the ultra-powerful Chandra X-ray Observatory detect absolutely nothing from the nebula itself? Where were the missing X-rays? Well, combining data from the FUSE Ultraviolet Observatory and the Chandra X-ray Observatory finally revealed something totally unexpected. Instead of a closed, spherical shell creating this superheated shockwave, the nebula actually contains an open, biconical cavity. Imagine a giant hourglass shape extending all the way to the edges of the gas shell. This open cavity acts basically like an exhaust pipe, allowing that incredibly fast stellar wind from the white dwarf to escape freely into space without violently shocking the surrounding gas. The researchers summed up this crucial point perfectly. Because of this open, biconical structure, the gas of the Skull Nebula isn't shock-heated to millions of degrees. Instead, it remains a relatively cool, photoionized plasma. It's glowing simply because it's basking in the intense ultraviolet radiation of that central, blistering white dwarf. The open shape of the cavity essentially acts as a massive cosmic pressure release valve. So, the next time you look up at the Cetus constellation tonight, gazing toward that faint, eerie glow 3,500 light-years away, it really leaves us with a thrilling thought. We've managed to decode the biconical cavities and the triple-star engine of the Skull Nebula. But what other bizarre, fascinating secrets, hidden structures, and complex high-speed dances are just waiting to be discovered in the chaotic lives of star systems across our universe? Well, that is a mystery for our next explainer. Keep looking up and keep questioning what you see.